We're off and running.
Like I heard.
Chapter 21. 22. Magnetism. Interesting that we'd be studying magnetism the week of Valentine's Day. What day is Valentine's Day anyway? Thursday? Tomorrow's my wife's birthday. No, Thursday's my wife's birthday. So tomorrow is the 14th. Okay. Tomorrow's Valentine's Day. 15th is my wife's birthday. I got to keep those straight. Not really, because she just considers them the same day. Just 2 days where she's supposed to be spoiled. So we got to figure that out.
Come on, man. He's gonna throw himself on the bus.
Okay, so dang it, I thought I went to the right chapter, but apparently I didn't. 22, magnetism. All right, we've got 11 sections to get through this week. Fair number of things to do. The Aurora Borealis. Aurora Borealis is something you can actually see it from Nebraska sometimes. It's not often, but every once in a while it sneaks down into northern Nebraska. You can definitely see it up in Alaska and northern Canada. There's a similar thing that happens down on the South Pole, but not many people live that far south, so not many people talk about it. But what it is the magnetic field of the Earth is pointing towards the poles of the Earth at the North and South poles. And charged particles out in space get captured by the magnetic field. And as they get captured by the magnetic field, they kind of spin into, they have a spin of death down. It's like going down a toilet bowl or something. They spin in around this electric field down towards the Earth and bombard the North and South poles with all these cosmic particles. And as they do this, they glow. And the reason that they glow is because they're accelerating, because they're going around in tight little spirally circles. And accelerating charges give off light. That's something that was explained by Einstein and observed by many others, observed by many scientists of the late 19th century. Charged particles glow and they accelerate. So that is an effect caused by the magnetic field of the Earth. The interesting thing about the magnetic field of the Earth is that the north pole of the Earth is actually the south magnetic pole of the Earth. And the reason for this is because when they back in hundreds and hundreds of years ago, when they were first understanding a little bit about magnets, they created the first compasses by floating a piece of wood with a piece of magnesite on the top of it. And they would float this in a little bowl of water or something. And they noticed that when you did that, the piece of wood would rotate and always point in the same direction because of this magnet that was floating on the wood, with the wood. And they called that north, and they called that end of the magnet, that end of that piece of material, they called that the north end of the magnet, and it pointed north all the time. But it turns out that the north end of a magnet actually lines up with the south end of a magnetic field. It's the north end of a magnet is attracted to the south end of another magnet, in other words.
That's the side of the electron moving.
So the Earth is a great big magnet with two poles, a north pole and a south pole. Our compasses on Earth, their north poles of our compasses are attracted to the south pole of the Earth, which is actually the thing that we call the North Pole. So the north geometric, or the north geographic pole of the Earth is the south magnetic pole of the Earth, and the south geographic pole of the Earth is the north magnetic pole of the Earth.
So nobody should make anything until they have a perfect understanding of the way it works.
Well, that's kind of, yeah, you would have a hard time making any kind of advances if you made a statement like that, but, you know, maybe we ought not to be so traditional once we figure things out. Magnets have this very interesting feature that they always have at least two poles. Always. You cut a magnet in half and you'll just create two magnets with two poles each. You won't create two magnets with one pole each. It's the way they are. And it's something that we are trying to understand as we go through the theories of very fundamental physics. And we think we understand, but our understanding is completely based on theory and conjecture because we have no way of proving what we think we understand. The only time that we think there might have been a magnet that only had one pole was maybe at the very beginning of the universe, right there at the beginning of the Big Bang. And that's a possibility, but still we don't really know. We can't see that yet. Hopefully we'll be able to see it with our new telescope we're putting up in the sky. Are you familiar with the new telescope they're putting up in the sky? It is called the James Webb Telescope. James Webb was one of the major players in early NASA history and ran NASA for many, many years. And the James Webb Telescope is about 10 times bigger than the Hubble Space Telescope. And so this gives you an idea of the size of the telescope. Oops. Let's see, they compare it to the Hubble Space Telescope here somewhere.
It looks like a coffee.
Excuse me. Anyway, one of the mirrors, so here's the James Webb, this is what the James Webb Telescope looks like right here. Let's pick a good picture.
There's a picture of people next to
So here's a nice picture of the James Webb Telescope. One of the mirrors on here is about the same size as the mirror on the Hubble Space Telescope. And you notice that it has, the Hubble Space Telescope is almost two of these actually. But it has so many more mirrors than the Hubble Space Telescope. And of course it would be virtually impossible to lift this telescope into space if it was like the Hubble Space Telescope all in one piece in a big tube like a traditional telescope. So this one is actually like an origami telescope. Everything in this folds down into something smaller than the Hubble Space Telescope. All of the mirrors fold down. That's why they have several different mirrors. They all fold down. This detector or this mirror array and the detector array all fold down. This is all shielding to shield it from cosmic radiation from the sun. That all folds down. It all folds up in this really tight package so that it can be fit on a spaceship, and it's also much lighter this way. They can fit it on a spaceship. You can see the size of this thing. It is impressive. It is impressively large. Well, here's the comparison. You can see that the Hubble Space Telescope, is quite large because it's got this great big tube associated with it. But the mirror on the back here is only about I think it's 1/8 or 1/7 the size of this mirror. So, and the mirror is everything with the telescope. The bigger the mirror, the more light you can collect, the further you can look out. You can look at dimmer and dimmer objects. But what's most important about this is that when you're looking further and further into space, you're looking further and further back in time. Even just looking at the sun, you're not seeing the sun as it is right now, you're seeing as it was 6 minutes ago. And the sun is fairly close. But if you're looking at something that is light years away, you look at Andromeda or something that's light years away, you're looking not at Andromeda now, but has what it looked like years ago. And if you look even further out, the Hubble Space Telescope could look at things that were like 5 billion years ago. So the Hubble Space Telescope is looking at the universe as it was 5 billion years ago. They're thinking that the James Webb Telescope might be able to go 10 or 11 or even 12 billion years ago, which is almost the beginning of the universe. The universe was a baby back then. It was only a couple billion years old. So that's the whole idea of this telescope, is to look way back there. And one of the things that they'd like to know is magnetism. Is magnetism something that started off as a single pole thing? Is it, I mean, the mathematics says that it should, the theory says that there should have been something like that way back then, but we don't really have any evidence of it. So this is one of the things that we're doing in physics today. This is one of the kind of the big deals in physics today. Where is my book? Somehow I lost my book. There we go. Nope. There we go. Okay, so anyway, magnetic poles. And so here they show that the magnetic pole, they show that the Earth has its magnetic south pole at the geographic north pole. But it's not exactly there. It's tilted a little bit. And the magnetic field of the Earth has changed many times over the course of its history. And that can actually be seen in the geological formations of the Earth, because the geological formations of the Earth, those that are magnetic, they actually form in a way that lines them up with the magnetic pole of the Earth at the time of their formation. Like this liquid rock is often magnetic, and liquid rock down, as it comes up towards the top and solidifies, it will solidify pointing in the direction of the magnetic field, or pointing opposite the direction of the magnetic field of the Earth. And you go back, digging down through the Earth crust, you find different rocks at different depths pointing in different directions. There's nothing that says that the magnetic poles of the Earth have to point north and south, or south and north. They've pointed east and west before. And on different parts of the Earth, they point all kinds of directions. The magnetic field of the Earth is by no means a constant, and by no means is it anything uniform. It's really messy, actually. And that has partially to do with just formations on the Earth, and partially to do with what's causing the magnetic field of the Earth to be a magnetic field. And that's another mystery. We're not really sure why the Earth has a magnetic field. We're not really sure what creates the magnetic field of the Earth. There have been a lot of theories over the years. For the longest time, they just figured it was the iron core of the Earth was rotating. Well, we have no real evidence that that is true. And in fact, some of the evidence that they're getting is starting to show that that might not be true at all. That we might not have any rotation really in any appreciable rotation besides the normal rotation of the Earth in the core of the Earth. That might not have anything to do with it. Now the prevailing theories are a little more convoluted, a little more complex, but very interesting, and having to do with plasmas and other things, high energy, high pressure plasma at the center of the Earth. I'm not sure if that's the best explanation. I'm no expert by any means. But anyway, magnets do have this very interesting and very mysterious feature that they always have at least two poles. They can have more. You can have a magnetic field with 4 poles. You can have a quadrupole magnet and other types of magnets. And the poles, I do believe they always come in even numbers, yes. There are different kinds of magnets. One of the more common types of magnets was called a ferromagnet. Ferromagnets are magnetic materials that are iron-based or iron-like materials. Iron is a material that easily magnetizes. Sorry. Sorry. Iron is a material that easily magnetizes inside of a magnetic field. And there are other materials that do that as well. Nickel is one of those materials that easily magnetizes in a magnetic field, and other materials. And the reason for this is because there are groups of atoms inside of the material that can kind of magnetically polarize in a magnetic field, and then they'll stay that way for a while. They'll kind of lock themselves in that way. And so ferromagnets are these kinds of magnets that you can create a magnet from these materials. There are permanent magnets. Permanent magnets are materials that are magnetic because they are permanently locked in at the molecular or atomic level, or whatever, small levels. they're permanently locked in so that they're creating this magnetic field. And it has, I mean, the magnetism is something that just plain and simply is kind of a mystery. We don't really know what causes it, but we know that it is an atomic feature. It's something at the atomic, subatomic level, the nuclear level, really. It's at the nuclear and the atomic level. And again, it comes down to theory. A lot of people said, well, it's because the electrons going around and around the atoms. Well, we again have no evidence that electrons move at all. We have absolutely no evidence. In fact, we know that electrons go from one place and then go to another place, but there's absolutely no evidence that they actually travel in between those two places. In fact, all of the evidence says that they never do. All of the evidence says that electrons just exist in one place and then they suddenly exist in another place within an atom. And so movement, when it comes to these things, is kind of goofy. And we're going to start to learn about a lot of really strange things that we can't explain because we have no evidence. The evidence that we have does not support the theories that were first given, so we've created new theories. So anyway, so permanent magnets, materials, there are many materials out there. One of the more popular ones these days that you've probably heard of is neodymium. Neodymium is neodymium. Neodymium. This is the word right here, neodymium. Neodymium magnets are the rare earth magnets that you've seen a lot of. They're very, very strong magnets. They use them all. I mean, tiny little magnets that can really hold a lot of. They're very, very strong in their magnetic attraction. If you're messing around with really strong neodymium magnets, you can cause damage to yourself and to others because they can snap together really quick and pinch off skin and other things. They're kind of dangerous. They're also really dangerous to other things like electronics and things. The popular idea that magnets are going to change your health or cause bad things for your health or good things for your health is completely without evidence, completely without any kind of basis in science. Our bodies are not affected by magnetic fields in any appreciable way. We're around magnetic fields constantly, aligning our molecules in a particular direction with magnetic fields in our clothing or necklaces or whatever else is bogus and bunkus. There's absolutely no science involved. It's just witchcraft of crazy nutbags. Who? Oh yeah, definitely. Science is not their forte. There's nothing about it that is scientific.
I just wanted to clarify.
I'm more than happy to be clear about it. This is a nice little demonstration of what it looks like when you have a piece of material that is less magnetized or more magnetized. Materials that are less magnetized will have these domains or these sections of the material that have a magnetism to them that are pointing in kind of random directions all over the place, so that overall the magnetic fields all cancel out and there's really no magnetic field going on. But when you have more of those domains pointing in the same direction because you either magnetize the material, putting it in a magnetic field if it's a ferromagnet, or if it's a permanent magnet, this happens as well, where most of them are pointing in the same direction, or maybe even practically all of them, then you get an overall effect of having a magnet, having a magnetic field caused by these domains that have magnetism all pointing in the same direction. Ferromagnets do have unfortunate problems that they can be demagnetized as well as magnetized. They can be demagnetized a couple of different ways. One way is you can just disrupt all those domains. You can just hit it with a hammer, and shaking it by hitting with a hammer or something will knock those things out of alignment again. Also, if it's not in a magnetic field. If it's in a magnetic field, if you've put that magnet in a strong magnetic field and you tap it with a hammer, they'll all shift and line up with the field. But if you take it out and have it around no magnetic field, they'll just rearrange themselves randomly and unmagnetize. But also heat causes ferromagnets to lose their magnetization. You get to a certain point, as they get so hot, these domains move on their own, and then they lose their direction unmagnetized.
Caused by the extra movement caused by heat?
Yes, that's exactly what it's caused by. So the extra movement from the heating of the material moves those domains and randomizes them again. And that the Curie temperature is the temperature above which a material just cannot be magnetized anymore because it's just moving too much. And that does happen. For iron, that's 1043 Kelvin, 770 degrees. So very warm. Some materials become really good magnets at really low temperatures because of another quantity, another phenomenon. And so there's another type of magnet called the electromagnet. Electromagnets are created by putting a current through a loop of a material. And it doesn't matter what the material is, you can create an electromagnet with well, the material should be a conductor, or at least conductive enough to support a current. But if you put a current through a loop, it creates a magnetic field, and that is called an electromagnet. And you can enhance that by wrapping your loop of current-carrying material around a ferromagnet, because then the magnetic field that you're creating through your loop will actually create a magnetic field in the ferromagnet and make it even stronger magnetic field. Or you can put it through a material that is very, very cold. And when you make materials, conductors, very, 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 very cold, they can really support a lot of current with very low resistance. And there are certain materials, which we call superconductors, that absolutely have zero resistance when they're below a certain temperature. Usually it's around 3 Kelvin, very, very cold. So you have to cool them with liquid helium, but that's how an MRI works. In an MRI machine, you have this big circle that you go inside, and that big circle is made of a superconducting material surrounded by liquid helium cooling machines. And if you've ever been in an MRI room, which we will hopefully have a chance to go visit this semester, first thing that they do before you go in the room is they make you remove everything metal from your person before you go anywhere near the room. And sometimes they'll let you hold a lanyard with keys on it at the doorway and watch the keys point towards the MRI machine, because the magnetic field is pulling your keychain. They're not even pulling the keys, because most keys are not magnetic, but just the keychain ring is enough because it's so powerful. But the current that's going through there, they have a very, very high current, and because that has no resistance. And they started that current 7 years ago in the MRI here in North Platte, I think, or 5 years ago or something like that, and it's still going because there's no resistance. It has absolutely no power dissipation. It doesn't lose any energy, doesn't lose any current. It just keeps going, round and round and round and round. And that thing is always on. And turning it off is a real pain in the butt, and you have to essentially warm it up and allow the heat to dissipate slowly. And then you have to start all over again, start it up again. So, because magnetic fields have always 2 poles or more, the magnetic field always comes back and loops around on itself. Very similar to electric fields, but not the same, but similar. Magnetic fields go from one pole to another pole. Remember, in electric fields, the electric field would go away from positive charges and go towards negative charges. In magnetic fields, it leaves your north poles and it enters the south pole, and it loops around so that the same field line always leaves one side of a magnet and enters the other side of the same magnet. That is always the case in magnetic fields. That's another one of the peculiar features about magnetic fields, is the magnetic fields can never just leave and go off into infinity like electric fields could. Electric fields could leave a positive charge and just go off forever and never encounter anything else. Magnetic fields, not so. Magnetic fields always loop back around to the same magnet, and they start where they end where they started. In fact, the magnetic field goes right through the center of the magnet, which you can see. This right here is a electromagnet, some coils of wire, and they've sprinkled some iron filings on here to line up with the electric field. And you can see line up with the magnetic field. The magnetic field goes right down the center of these wires where that current is, and then it comes out and it goes around, and you can see that it's going around and it comes back in here. So the shape of these fields is unique, different than the shape of electric fields in many ways. And magnetic fields are used practically all kinds of different ways. Here they show a magnetic field, they show a magnetic disk. Of course, this is a bit out of date. It's a floppy disk or something like that, where you have this magnetic disk, which is made of a kind of a ferromagnetic material that can be magnetized in a magnetic field. And then it has an arm out here that has a little electromagnet on it that writes little, essentially puts data on the disk. So it magnetizes parts of the disk and demagnetizes other parts of the disk. And those magnetizations are a code for the computer that gives it the data that it needs. And this is how hard drives work in your computers for the most part. If you have a computer that has a solid state drive, it doesn't work this way. But hard drives, the ones that spin up and have all the sound associated with them, they do work this way. And we're getting more and more away from magnetic memory storage. Magnetic memory storage is still the cheapest form of storage, but solid state is so much more stable and fast. It's so much faster to retrieve your information. Because to retrieve your information from here, you have to have a head, you have to have this head on this arm here that goes out and finds the data and reads the data and then writes the data, and that's all mechanical. And mechanical stuff takes time to do. So to read off of a floppy disk, when I was in college, reading things off a floppy disk can take minutes or even hours in some cases, depending on how much you were reading off. Whereas if you're reading off of solid state, it's essentially just a microchip where you've stored some digital data and you just go and get it and pull it right off, no problem. And it's all done electronically instead of mechanically. This is also done in old tape recorders and tape players where they'd have the recording and reading head. The recording head would magnetize the tape. The reading head would just detect the magnetism on the tape and read the information off of there. But there's many other uses for magnetism, even when we're not talking about storing data on tapes or disks. Many uses of magnetism still today, and it's not going away anytime soon. This statement here, where it says electric current is the source of all magnetism, is not correct entirely. In fact, it's probably not correct at all. But that's okay. We'll give them a pass because they're trying to make it understandable. But a better way to say it is that electricity and magnetism are always connected. There's no such thing as one without the other. There's always, and to the point that in physics, we don't call it electricity and magnetism. We call it electromagnetism because it is one and the same thing. And this is something that was worked on for years and years and years back in the 1800s. They were trying to figure this out. And finally, somebody came along and made the connection. And it was who's the guy that's named? What's the name of the equations on your T-shirt? I forgot. Oh, Maxwell. It was Maxwell who figured out the connection between all of the electrical stuff and all the magnetism stuff. He put it all together and discovered that electromagnetism was actually always also responsible for light, and that light is just another subset of electromagnetism. And Einstein took it from there and connected it to all kinds of things. So it's a really important thing getting into magnetism, because this is going to open the bridge and the gateway to modern physics and so many other things that are very interesting today. Let's take a look at this, see if it's any good. Should be a good one. Yeah. Okay, so here we've taken a magnet, we've got our magnet here, and it's showing the field lines. And the way it's showing the field lines is it's putting a bunch of these little compasses out there. So each one of these little things represents where a compass would be pointing if you stuck it out here. So if you stuck compasses right in front of the South Pole, they will point with their North Pole, the red poles, towards the South Pole. And on the other side, the South poles of the compasses will point towards the North Pole. And in between, they kind of do the in-between thing, right? And we can move this around and show how it changes things. And this big compass over here is affected as well. Very interesting stuff. So if it's the Earth, right, we get a different thing going on, but it's still very similar. So what happens if you put your compass near the North Pole of the Earth?
No matter what, it's going to point away from, if you're on the magnetic South Pole of the Earth, no matter where, what direction you go, it's going to tell you to go inside.
Compasses are not very useful when you get close to the North Pole. And if you hold your compass flat, it actually will just kind of spin in circles. If you hold it straight up and down, it will point straight down towards the ground. That's south, right? And that's useful, I guess. Down is south. That's true. Not very helpful, but it's definitely true. But if you hold it flat, if you hold your compass parallel to the surface of the Earth at the North Pole, it won't detect a field really. It won't line up with the field in any way, so it'll just kind of spin around randomly. Same on the South Pole.
And wouldn't it constantly be having slight shifts, so wouldn't your compass just be absolutely wrong?
Yeah, your compass is just not really worth very much up close to the North Pole or the South Pole. So yeah.
I know I bought a Garmin GPS. The way that those work
Well, see, the Garmin GPS works very differently, and we'll learn about how they work later in this class. But they work on principles that are both very ancient but very modern as well. The Garmin actually works pretty much the same as a sextant. Yeah. I mean, if you had a sextant and a really good clock, you could figure out anywhere you were on the Earth using those. And that's exactly the principle that you're using. Well, not exactly, but very similar to the principle that you're using with a GPS. But instead of having a very fine clock on your ship and a sextant, you have a really good radio that communicates with a really good clock in Colorado. And you have a really good detector that detects satellite signals from space. And that's all a GPS is. A GPS itself has nothing in it that can tell you where you are. But it can communicate with things that can tell you where you are. So
I'm all for it.
yeah, it works really beautifully. And I still remember the first time I used a GPS as a Boy Scout in like 1989, maybe. I mean, it was a long time ago, maybe 1988. This thing was the size of a briefcase, and it had a huge antenna. And we had to wait like a half an hour for one of the 3 satellites that was allowed for civilian use to come up over the horizon, because there were very few satellites available for civilian use at that time. All the rest of them were just for military use. And the only reason my Scoutmaster had access to this was because he worked for Chevron as an oil guy. He was the one that went out looking for oil all over the world. And so he had access to this stuff because he was important to the oil companies. Is Chevron even a company anymore? I don't
It's
think
still
so.
a company, they don't make the cars.
They don't make the toy cars. Anyway, so here's what electromagnetic looks like. You make a loop of wire connected to some kind of source for current, and then the magnetic field goes through the loop, it turns out. So it's different than a permanent magnet or a ferromagnet in that the magnetic field doesn't go through the material, but it still has a north and south pole. It's like a virtual north and south pole.
Yeah, it doesn't even have to have a piece of metal in between of it.
Nope, doesn't have to have anything in between. The magnetic field will go right through. Yep. And so it can be very useful because then you have a magnetic field in between the wires that can be used for things as well. And we use electromagnets for so many things. You've probably heard, if you've ever worked on cars, you've probably heard somebody talk about solenoid of some kind.
What?
A solenoid.
Cylinder.
Yeah, solenoids this is what a solenoid is. A solenoid is an electromagnet that is designed to create a magnetic field down the center of a wire, and it usually has something that is in that space that is going to move. Not always, or it's going to act in some way when that magnetic field is
That's the only
created.
way old motorcycles or dirt bikes get electricity.
That's right. So solenoid coils are used for many, many different things. They're very useful. Not only are they useful, in like cars, motorcycles, and other things, but they're useful in your cell phone. You have solenoid coils in your cell phone. Without them, it would not work. So we'll learn more and more about how that is, how these things work. And you can also create an AC magnetic field that changes direction as you change the direction of the current. Because the current goes one direction, the magnetic field is one way. Current changes direction, it goes the other way. And this can be very useful as well. Extremely useful. So in this case, your magnetic field's one way back and forth, back and forth, back and forth, constantly changing. So lots of different magnetic fields out there. Here they talk about magnetic monopoles. No magnetic monopoles, in other words, a magnet with one pole, have ever been observed. We assume that they cannot exist, but we theorize that they maybe could have at some point. But so far, we've never observed one. Another reason that they want to look way out into space is to discover new phenomena. They want to see if there are some weird things going on in space where things like magnetic monopoles might exist. You know, we've not looked far enough into space to see anything super weird, but we've already seen some pretty weird things.
When is this,
So-
when is that going into space?
Good question. I think it's this year or next year.
Well, that's going to be pretty revolutionary. Because the Hubble, whenever it went into space, that kind of redefined the
Yeah.
Hubble.
And we've put in 3 or 4 telescopes into space since the Hubble Space Telescope, and good ones, big ones. But they've been specialized telescopes designed to do specific things, and not. I mean, the Hubble Space Telescope is a visible light telescope, so it's designed to look at things that we could see with our eyes anyway. Other ones are up there for soft X-rays. Others are for other. You know, they're looking at various different spectrums. And the James Webb is going to look at primarily the infrared band. It's going to look at light that will travel a little further than visible light on average. So it's looking further back into into space. Let's see.
So basically, the entire point of this telescope is to see how far back in time.
Yeah, that is pretty much the idea.
That's
2019. Huh. I wonder if they'll launch it on the new rocket that just went up, because it's probably the only rocket that can lift it up into space.
That SpaceX deal?
Yeah.
cool.
Because it's my understanding that they do need a bigger ship to launch this, and they hadn't had a. Oh no, I guess they do have one that they want to put it on, Ariane 5.
They should just hire SpaceX to launch it.
Yeah, they might, because this one is not done by the United States. This one is a European space agency, unless they've already made a contract for it. But anyway, and this one's not nearly as powerful as the other one. This will take it up to. Anyway, yeah, I hope that they go with the SpaceX, because it'd be good to keep it in the family, right?
On top of everything else, the SpaceX shot, it's just look better.
Well, and they put a car in space. Come on, it's just cool.
Car or rocket man, that's the coolest thing ever.
Their video feed petered out after a few hours that first day. I mean, I think it was 18 hours. It petered out, so they don't have any more imagery for it.
Did it die?
They just ran out of battery power. They didn't plan on it being forever, apparently. I thought that they would connect it to a solar panel or something so you could watch it go off into space, but apparently not. Okay, so magnetic fields, they point away from the North Pole and they come loop around and point in towards the South Pole. So we already mentioned that, but just to reiterate. With loops of wire, when you have a loop of wire, a loop of current, we use a trick to determine which way the magnetic field is going. And we've used this trick before when we talked about torque, the right-hand rule. In this case, the right-hand rule, you're going to take your hand and you're going to curl it around in the direction of the current. So your fingers, make your hand like a high five kind of hand,
Yeah.
and you curl your fingers, not your thumb, but your hand and your fingers around the direction of the current. So in this case, my hand would be going around the back and my fingers would be coming towards the front as I curl around that. And I'm going to turn on my camera so people can see what I'm doing here. That's not what I want to do. Here we go. So if the current is doing this thing, so we have a current that's going around like this, right? And I take my hand and I curl it around the back and my fingers coming out of the board like this, and my thumb is then pointing up, and that tells me which way the magnetic field will be pointing. My thumb, if I curl my fingers in the direction of the current, around the current, my thumb will point in the direction that the north that the north pole of the magnetic field is, or in other words, the direction.
Throw your hand around with the thumb
So if the current was going the other direction, this direction, right? Instead, I would curl my hand this direction, and that magnetic field would be pointing down. That's the direction of the north pole field of the magnet, right?
Okay, so the north follows the right hand.
That's right. The right-hand rule shows you the direction that the field is coming out of the North Pole. So the magnetic field, and magnetic field we use B for that. Thank you to the Germans. The magnetic field of this one is pointing upward here. It comes all the way around and points inward here. Okay. If the current is going the other direction, right-hand rule points down. Then the magnetic field is going this way, and it comes all the way around and comes through here.
So the north is the positive.
Well, don't think of it as north is positive, okay? But north is the direction that the field points away from the magnet.
So magnetic field is not a vector.
Magnetic field is a vector, but it's not positive. We're not thinking of it in terms of positive or negative. Remember, vectors are positive and negative not by which way they're pointing, but which way your coordinate system is pointing, right?
So that's away from the magnet.
Away from the magnet means north. That's the north pole side of the field, right? Or that's. So anyway, but there's another effect called the lens. There's an effect called the lens effect. It was discovered by a guy named Lenz that shows that there's actually a magnetic field around any current, even if it's not in a loop. So if you just have a wire with current going through it, just any old direction, you have some wire and it has a current going through it in this direction. It turns out that there is a magnetic field in the vicinity of this wire too. And it's actually what creates the magnetic field of a wire in a loop. But the magnetic field here is kind of strange. But we still use the right-hand rule. But when it's just a wire going in some direction, we use our thumb in the direction of the current, and our hand will curl around the wire in the direction of the magnetic field. So the magnetic field is actually going around this wire. It's coming out of the board on the top. We'll use points, like the points of arrows, to show it coming out of the board. And it's going into the board on the bottom. We'll show the fletchings of the arrows going in. And it's forming these loops around the wire this way. Okay? And so if we put our thumb in the direction of the current, it's coming out on the top, and it's going into the board on the bottom. And if the current was going the other way, it would be just the other way. Wow, that's really not very visible up there, is it, on the screen? Sorry. It is dark, because we don't have lights on the board right now. But that's shown in the book as well. Let's go back to the book and see this. So here is that loop of current with the magnetic field coming out the top and around and back in the bottom. And here's the line of current where the magnetic field goes around it in these loops. So the magnetic field forms circles around the wire. And the right-hand rule for this one is you put your fingers around, you loop your fingers around the current. Your thumb shows the direction of the field. For just a line of current, you put your thumb in the direction of the current, and your hand will curl around in the direction of the field. And here's how they show this magnetic field coming out of the page and going into the page. And we're going to use these. We're going to use this quite a bit. This way of showing which way the fields are going. Now, very similar to electric fields, representations of electric fields, when we draw magnetic fields, we're going to draw them so that the strength of the field is proportional to the closeness of the lines, just like with electric fields. So if the lines are closer together in a particular situation, that means a stronger field. If they're further apart, it means a weaker field. If we go back to this, let's see. If we go back to magnets and electromagnets demonstration here, and we show the field inside the magnet, you can see that inside the magnet, the fields are pretty close together, and that's where the field is strongest, is right in the magnet. Out here, they start to spread apart as they go around, and it's definitely weaker. If we go to the electromagnet, you can see that as well. Right through here in the middle, they're a little closer together. Out here, they start spreading apart more and more. Gets weaker and weaker. And it's much more stark contrast in real life than that. In real life, magnetic field really drops off as you go further and further away from it.
Is it exponential?
It is,
Like,
I think it's more than that actually.
uh,
I think magnetic field drops off more than electric field does. Which was, where'd my book go?
gravity and electric field both drop off exponentially, correct?
I'm sorry, what?
Gravity and electric field both drop off exponentially, right?
Yes. They both drop off as distance squared.
And that's not true of magnets?
And that's not technically exponential. It's just they drop off as distance squared.
Right.
Okay, so so now let's look at some of the other things that have been observed throughout time. One of these things that's very important is this idea that a charge that encounters a magnetic field while it's moving. So an electrical charge moving through a magnetic field feels a force. If it's not moving, it doesn't feel a force. But if it is moving, it does feel a force. Now the other thing that's interesting is that if the charge is not moving, but the magnetic field is changing, it feels a force. So really what's going on is that a magnetic field can exert a force on a charge if the charge is moving, if the magnetic field is moving, or if the magnetic field is changing. Any of those things. If any of those things happen, then the charge will feel a force of some kind. But it's really funky. The strength of the force is fairly straightforward. You take the amount of charge, Q, and you take the speed that it's going, V, and you multiply by the magnetic field, B, and then you multiply by the angle between the velocity and the magnetic field, sine of theta. So theta is the angle between the field and the velocity.
Q is the charge.
Q is the charge of the electric charge.
Okay, Q is the electric charge.
V is the velocity of the charge, or the speed of the charge, actually. B is the magnetic field value. And
That's just the angle.
And then the angle between the magnetic field and the velocity, you take the sine of that and plug it in here. And that will tell you how much force this charge is going to feel. We call this the Lorentz force. And magnetic field is something that we measure. It's measured in, we have a couple of different units for it. You can measure it in Tesla, which is the standard unit. If you're using everything normally like we do when we measure things like meters per second and things like that. It will measure in Tesla. 1 Tesla of magnetic field is huge. So the Tesla unit is a huge amount of magnetic field. We often use, instead of Tesla, we often use I can't remember. There's another unit we use sometimes that makes it a little more manageable number. But anyway, we'll use Tesla. And a Tesla is 1 Newton per coulomb meters per second. You can see that right there. Let's see, do they have a...
They give you Gauss.
Oh, Gauss, yeah.
Yeah.
They use Gauss as where is it though?
That's,
Oh, there it is. So 1 Gauss is equal to 1/10,000th of a Tesla. So 1 Gauss is much more like the magnetic fields we experience. Like the magnetic field of the Earth is 0.5 Gauss. It's half of a Gauss. So that's a much more manageable number to deal with rather than 10 to the minus 5 Tesla. You know? But Tesla is the standard unit when you're using newtons and meters and seconds and coulombs and everything else. And so magnetic force is calculated this way. You can also calculate the magnetic field by measuring the force on a known charge going at a known speed just by rearranging this equation.
So 0.5 Gauss is equal to 9.8 meters per second squared.
No. 0.5 Gauss is equal to the amount of is the amount of magnetic field that we feel on the Earth on average, on the surface of the Earth. That's the amount of magnetic field that is on the Earth. It's a very small amount, actually, but magnetic fields generally are pretty small. The strange thing about this is the direction of the force that a charge feels when it's in a magnetic field. The direction that it feels is not the same direction as the direction of the field. The direction of the force is not in the direction of the field, in other words. In fact, the direction of the force will be perpendicular to both the field and the velocity of the particle. How is that going to happen? Well, let's think of it like this. You have a particle that's going along in the direction, this green direction right here. And the magnetic field is pointing in this direction here. So the magnetic field is pointing, let's call this north and let's call this east. The particle is going east and the magnetic field is going north. That's kind of a little like, would be like on Earth, except the magnetic field of the Earth is actually pointing south, but that's okay. We'll just pretend we're on a planet where the magnetic field of the planet points north. So you've got this field that's pointing this north and you're moving east. You're actually going to feel the force that is going to lift you off the planet. It's going to increase your altitude. You're going to fly up. Right? And the direction of this is determined again by the right-hand rule. In this case, the right-hand rule says that we put our thumb in the direction of the speed of the particle, or the velocity of the particle. We put our fingers in the direction of the magnetic field of the particle, and our palm will point in the direction of the force on that particle, but only if that particle is a positive charge. This rule works if it's a positive charge. If it's a negative charge, it's just the opposite direction. So the direction will be out the back of your hand instead of out the palm of your hand. So that's the right-hand rule. We use lots of right-hand rules. So things to remember. And during this chapter, during your homework, you will be doing this thing all the time. You'll be doing right-hand rule with one hand while you're trying to write with your left hand if you're right-handed. If you're left-handed, you have an advantage. You can write with your left hand while you're doing the right-hand rule. But if you're right-handed, you're going to have a disadvantage while you put your pencil and pen down and figure out which direction things are going. And it's something that you're going to do a lot during this chapter and the next chapter.
Why didn't they make it the left hand?
You can use your left hand, but everything will be exactly the opposite and it'll confuse you.
So, I can the left-handed scientist.
The reason that they didn't is all because of Benjamin Franklin. We can curse Benjamin Franklin once again.
Okay.
If he chose the electron to be the positive particle instead of the negative particle, we could use a left-hand rule and all of us right-handers would be happy. But this is one of those instances where left-handers are happy and the right-handers get shafted. I did believe he was, actually. But he didn't know this was going to happen. Okay. So here is an example. We have a charged glass rod that is going to be moving to the west. So we've charged it up with 20 nanocoulombs of positive charge, and we're going to move it to the west in the Earth's magnetic field. We want to know how much force it is going to feel, which direction it's going to feel it. Well, first we'll calculate how much force it's going to feel. So it's moving in the west direction, and the magnetic field is in the north direction, which means the angle between the two is what? 90 degrees. What's the sine of 90? 1. That makes this easy, right? So it's just Q times V times B times 1. We're good. What's Q? 20 nanocoulombs. 20 times 10 to the minus 9 coulombs. What's our speed? 10 meters per second. What's our magnetic field? It's 5 times 10 to the minus 5 Tesla. That has to be put in Tesla. Cannot be put in Gauss. And then we multiply the amount of force. 1 times 10 to the minus 11 newtons. Not a whole lot of force.
Wait, does that mean that if we're measuring a scale at that point, it would seem lighter?
Well, it depends on which direction this force is.
If we're assuming that.
So which direction is this force going to be? Remember, you have something moving to the west, so west.
So that one's going to feel heavier.
So it's moving to the west, and the magnetic field is to the north. You put your thumb in the direction of the velocity, which is to the west. You put your hand in the direction of the magnetic field, which is north, and it's actually going to point down towards the ground.
So that one will feel slightly heavier.
That one will feel slightly heavier as it moves to the west, but so slightly heavier that it's not even measurable. It's times 10 to the minus 11. That's a tiny force, especially on an object that actually has some mass to it. If it was an electron, it would feel it. because an electron has a tiny mass, much tinier than that force. But a glass rod, anything that has a measurable mass that is easily measurable, will not feel that force at all. However, if it's a bigger object moving faster, you can actually measure these forces. You can actually measure these minuscule forces and use them to determine, for example, which direction you're going or how fast you're going. And this is actually something that was done by submarines. Submarines used what they called, what did they call this device? They called it a gravimetric sensor or something that essentially used this concept. The moving submarine is essentially a moving charge. There's all kinds of charged things on a submarine, and it's made of steel, so it's a moving charge anyway. And it's moving in a magnetic field, and as it moved in a magnetic field, it has this magnetometer on board that measures these changes, these minuscule forces and minuscule things on board the submarine, so they can tell which direction they're going, how fast they're going, and everything else, when they're turning and everything else. And they could navigate for a long time using those. And a submarine has 3 or 4 redundant systems that are all different, that behave in different ways. So they can check where they are using many different methods and kind of get a good idea on average what they're doing. And that's just one of them.
How would they get off of the 90 degree?
What?
Like what instances would it not be a 90 degree?
Well, what if it was moving northwest? What if instead of moving this way, it was moving this way? Then it would be moving. It was moving northwest, and you would still put your thumb in the direction of the velocity, which would be kind of this way, and your hand would still be in the direction of the thing. So you'd have a different angle between your thumb and your hand, and the force would still be down, but it would be less because the sign of the angle between your thumb and your hand would be a smaller angle. It would be 90. The sign of 60 degrees, for example, is 1/2 instead of 1. So you'd only have half as much force. What happens if you're going north on the Earth or south? You don't feel anything because what's the angle between your velocity and the field? 0 or 180. Which sign of 0 or 180 is 0, right? So if you're going in the direction of the magnetic field or opposite the direction of the magnetic field, you feel no force. You have to be going off angle from it
So
somewhere.
this is just a fancy way of describing Coriolis effect.
Nope, Coriolis has nothing to do with this.
You gotta shoot east to west for it to matter.
Well, it behaves similarly because the Coriolis force does have this east-west thing, but that's because of the rotation of the Earth, not the direction of the magnetic field. So the Coriolis force is completely caused by the rotation of the Earth.
Okay.
And this is caused by the direction of the magnetic field of the Earth. But you're correct in that it does behave similarly in that this way the more you turn away from the magnetic field, so that if you're completely turned 90 degrees to it, you feel the maximum force. And the more you turn towards it, you feel less and less of it. And that's very similar to the Coriolis force. So let's go down here and look at some examples of something you might see in your homework. What direction would this charge feel if it was a positive charge? Which direction would the force be? Get your right hands out.
See, that's coming out.
So what do we do? What do we do? What's the first thing? Thumb in the direction of what?
The vector.
Thumb in the direction of the velocity. Hand in the direction of the magnetic field. The direction of the magnetic field here is the orange stuff, and it's coming out of the page. So we point our fingers out of the page, and then our palm will point in the direction of the force. Which direction is the force on this one? To the right. Because our thumb is pointing down in the direction of velocity. Our fingers are pointing out of the page in the direction of, so we go down, out of the page, right? Down. Our fingers point out of the page with the magnetic field, and it points actually to the left if you're facing this screen. Right? So our palm points to the left. Thumb down, fingers out, palm points to the left. Right? How about this one? Magnetic field pointing to the right, velocity pointing up. So we put our thumb up, our hand to the right, our fingers to the right, and our palm points which direction? This and this. Our palm points into the page or into the screen. So the force would be into the screen for a positive charge. It would be out of the screen for a negative charge, right? Because it's just the opposite of that. How about this one? Velocity into the page and magnetic field up. What do you do with your thumb? Thumb into the page, fingers up. Which way does it feel a force? To the right. Negative charge? If it's a negative charge, to the left, right? Out the back of your hand. That's how you figure out the direction that the charge will feel its force. To calculate what it's going to, how much force it's going to, you use the equation. And you have to know the angle between, all these angles are 90 degrees, so that makes it easy, right? Okay. So that is our first equation of the chapter, the Lorentz force equation.
Not counting the equation to calculate the unit.
Yeah.
And no fan.
Excuse me.
There could be 89 digits.
Man, we're 5 sections in. This is sweet.
We're 5 sections in and we've got one equation.
22.5, force on a moving charge and magnetic field, examples and applications. So we're just going to do a bunch of different ones now. That's what we're going to do. This is a really cool, this is a drawing. I want to show you it in real life. If you're ever in Chicago, I think that's the closest bubble chamber to us. Bubble chambers are rather expensive to build and maintain. You have to have a lot of expertise to maintain them. And so the closest one to us, I believe, is at the Fermilab's accelerometer. They have a bubble chamber there. And what a bubble chamber is it's got a liquid in it in a very particular state. Yeah, here it is. This is an old paper. Anyway, I'm hoping that they'll actually show us the bubble chamber itself, but this is the bubble chamber. It's this great big spherical thing, but it's got a liquid in it that's in a very specific state, and in this case, I believe it is hydrogen, and it's I can't remember if it's in can't remember what the state is that it's in, but the reason what goes on in this liquid is it is able to track particles as the particles go through the chamber, and these particles are usually fairly exotic particles that don't that are very difficult to detect otherwise. You can't detect them any other way, and just don't show up in the universe very often. And so this includes things like antimatter. And when you're actually looking at the tracks, these little tracks that these particles leave behind, this is what you see. And inside the chamber, there's also a very large magnetic field imposed in the chamber. Actually, I'm not even sure if Fermilab's has anything besides Earth's magnetic field, but I think they do. I think they have a large magnetic field going from top to bottom of the chamber. So that as these particles are created, and most of them are charged particles, but as their particles are created, they actually feel a force. And usually that force causes the particles to turn. Now you can see some particles don't turn much. Some of them go straight through. Those would be particles that are not charged particles, because only charged particles feel a force in a magnetic field. But all these other ones are charged particles. But notice something interesting. There's no particle, and then all of a sudden, right at this point, there's two particles. That is what we call, that is the creation of matter and antimatter from energy. There was nothing before, just energy in that spot. But that energy created a particle of matter and a particle of antimatter. And those particles of matter and antimatter existed from that moment on. And you can see that one has a one has one charge and one has another charge. One felt a force in one direction, one felt another force in the other direction, right? So they weren't exactly the same particle. They had opposite charges, obviously, because that's the only thing that would make them go different directions like that. And there are many situations, many different places like that. Some of them have tighter circles. That means they're feeling a stronger force. That means they might have a bigger charge. It means they might have smaller mass. They would feel a bigger force, right? So you can actually start to figure out what particles these are by looking at the shape and the size of their path. This very small path here, or one of these bigger paths here. That's a really big path, right? And the reason that they do this at Fermilabs is because they're creating these exotic particles all the time in their accelerators. So they have these accelerators where they're smashing particles together and all these crazy things come out. And this is one of the things that detects what's happening there, is this bubble chamber. Some things just happen naturally. Some things are just natural occurrences. But many of these things are things that they actually cause to happen as well. So if you ever have a chance to go up to Fermilabs, you can see their bubble chamber and see the cool things they do there. They do a lot of cool things at Fermilabs. But this idea of giving a force to particles is extremely useful. We actually have a device here over in the chemistry department that is called a mass spectrometer. What a mass spectrometer does is it shoots charged particles of an unknown material into a strong magnetic field. And the magnetic field is well known. They know what the strength of the magnetic field is, and they know what the charge of the particles are when they go in, because they charge them a specific way. So the only thing that's going to affect how far they're pushed is that they don't know is their mass. And so the further they're pushed, the less mass they have, and the less they're pushed, the more mass they have. And so it depends. There's actually an interplay between the speed of the particle and the distance and the mass of the particle. So the speed of the particle and the mass of the particle, there's a ratio there. But they actually have a scale on this device that will tell you, oh, that is titanium or that is lead, because they know exactly where those things are going to land from their mass and the velocity that they would be given with the amount of charge that you give them.
All right, so it's like this for the top one, right? Force is coming off the bottom. So whenever you figure out your other thing, your fingertips, is that supposed to curl around or just go straight out?
So the right-hand rule says that you put your fingers in the direction of the velocity. Your thumb in the direction of the velocity. Put your thumb in the direction of the velocity, and you keep your hand open. You don't curl your hand for this one. You keep your hand open for this one. Put your thumb in the direction of the velocity. So in this case, I'm putting my thumb to the left, right? And then my hand is supposed to turn in the direction of the field. So I rotate my hand, my whole hand, around my thumb, like my thumb is an axis, so that it's pointing in the direction of the field. In this case, the direction of the field is into the board, so I rotate it all the way down. Is that right?
No. The point is just the point.
No, sorry, I rotate my fingers in the direction of the field. So I rotate my hand down so my fingers are pointing in the direction of the field. So the velocity is this way, and then I rotate my fingers until it's in the direction of the field, which is into the board.
Oh, you got me.
Right? Like that.
But I thought the field would become.
Oh, so for this one, since it had X's on the field, the orange circles are the field. The X's represent the back of the arrow, like the fletchings on the arrow.
What's the single point in the center?
The single point in the center is just the center of the movement.
Yeah, but I thought the F was the force. The force come off.
It is. It is. Hold on, let's get through this. So you put your thumb in the direction of velocity. Do it with me. Right hand. Thumb in the direction of velocity. So your thumb should be pointing to the right on the screen. Then you're going to rotate your hand until your fingers are pointing in the direction of the field, which is into the board. So it should be pointing this way.
Yeah, then the field's going
But
up.
wait, do what I'm doing. Then, if it's a positive charge, your force was up. But this is a negative charge. They told us this is an electron. So it's pointing out the back of your hand. So the force is down.
Okay.
And this one, it feels a force down, so it goes downward. And as it goes downward, its velocity changes. So now we do it on the side. Our thumb goes this way and the field is in, and then it feels a force inward. And then when it feels that force inward, it gets pushed this way, So now our velocity is this way, and our force is upward. And so in other words, the force constantly changes, and that's why we get rotational
Alright.
motion inside of a magnetic field.
So, velocity, force, field. How do you know which way the field's going?
The field is going into the board because that's what those X's represent. X's represent into the board, dots represent out of the board.
The X is into the page.
X's represent into the board, and that's why they put this B over here saying B in, B in. They're saying that's the magnetic field into the board.
And a negative charge, negative Q.
Yep. So if it's a negative charge, that means that the force comes out the back of your hand. The positive charge comes out of your palm. Right? So this is again the right-hand rule, but the interesting thing about magnetic fields is because of this right-hand rule, a charge that is going into a magnetic field will always end up going into a spiraling motion if it is not directly in the direction of the magnetic field or opposite direction of the magnetic field. If it's off kilter at all, it'll always end up in some kind of spiral motion because that force is always 90 degrees to it. It's like gravitational field in orbits, right? Why does the Earth orbit around the sun? Because the force field is always towards the center of its motion, and it's going the opposite direction. It's going in the direction 90 degrees to its force. The Earth is moving in one direction, and it's being pulled 90 degrees to that direction, so it orbits. And so charges coming into magnetic fields always go into these spirally, orbity kind of things. Now, if they go into a perfectly circular orbit, we know something about perfectly circular orbits. We know that the mass of the object going in a perfectly circular orbit times its speed around that circle divided by the radius of that orbit is the centripetal force. So you can actually set the centripetal force on the right side equal to the magnitude of the magnetic force on the left side, and you can solve for the radius of a charge's orbit inside of a magnetic field. So if you have a charge coming into a magnetic field at 90 degrees to the magnetic field, this only works if you're 90 degrees to the magnetic field. But if you have a charge coming in with a speed v, mass m, charge q, into a magnetic field with a strength b, that's the radius of the orbit. And guess what? That's how a mass spectrometer works. Right? So they know that for a particular charge and a particular mass, particular speed, and a particular magnetic field, they can get a particular radius. And you can know exactly what your radius will be for titanium, or exactly what your radius will be for strontium.
The charge in the field, velocity is the velocity of the what?
Velocity of the particle. It's the charge of the particle, the velocity of the particle, the mass of the particle, and the magnetic field that it's going into. B is the magnetic field. Everything here has to do with the particle itself, except for the B. So this is the mass of the particle going into the magnetic field. This is the velocity of the particle going into the magnetic field. This is the charge of the particle going into the magnetic field. And this is the magnetic field that it's going into. So if you plug in those numbers, you will be able to calculate the radius of the orbit of that particle once it enters that field.
If the velocity of the particle changes, that's about the only thing that...
Yeah, but in this case, we're talking about the magnitude of the velocity, not the direction of the velocity. In this case, the velocity will change because it will turn, but the speed will not change. Its magnitude will stay the same even if its direction changes. Just like the speed of the Earth around the Sun doesn't change even though its velocity is changing because it's changing direction all the time. Very similar thing. So, and the speed of a charged particle will not change if it goes into a magnetic field. It just won't. The speed of the particle will not change in the magnetic field because the magnetic field force will always be 90 degrees to its original velocity. So it won't change its speed, it'll just change its direction. It'll just push it in a different direction constantly in some kind of spiraling motion. And that's exactly what's happening with the aurora borealis. You have these particles coming in from space, and it's the particles that are coming in. Let me show a picture of the Earth again. Actually, let's see if there might be a good graphic online really quick. I'll bet you there is. Aurora borealis. So let's see if we can find. Here's a good picture of it. So the Earth. Let's see. That's not a really good picture. Oh, here's a good one. So the Earth has these magnetic fields coming out the bottom and back around the inside, and all these particles are coming in from the side. They're coming from the sun from the side. The particles that come in from above don't feel any forces from the magnetic fields of the Earth. But the ones that are coming from the side feel forces because they're 90 degrees to the magnetic field. So as they come in here, they get turned, and they actually get turned inwards towards the magnetic field, and they spiral around the magnetic field lines down towards the Earth. And it's the spiraling around those magnetic field lines that causes the glow. If they didn't go into that spiraling, spinning, orbiting kind of motion, they would never glow because they wouldn't be accelerating. But they do. They spiral in here, and that's what happens.
So if the magnetic field of the Earth was oriented so it pointed directly at the sun,
Shooting off in space.
Yeah, you'd see much less. And you'd see not only would you see much less because the magnetic field is not so strong at the equator, but you'd see it at the equator. Well, you could see some at the poles as well, but probably wouldn't see anything at all because there just wouldn't be enough strength and enough forces going on to really cause those things to accelerate in. But this is why you see this spirally motion going on with these things. That's what causes that strange effect, these weird things. There's another effect that's going on as well, and it has to do with particles colliding with each other, particles in the air colliding with the cosmic particles. That also causes some of the effect. That usually causes the kind of curtain effect that you see. But Aurora Borealis is a beautiful thing. I've never seen it. Someday, maybe.
let's go to Alaska.
Yeah. Old TV screens used magnetic fields to create the image on the TV screen, and we used to do this all the time. We used to mess with the TV screens by putting magnets near them. You could really screw them up. But it was fun. But here again, you can see this spiraling path of this particle as it comes in. It's got this spiraling path as it goes in there. You can see that here's a nice image of the spiraling path of the particles as they come in towards Earth on the Aurora Borealis. Incidentally, this is what protects the Earth from much damage from high energy cosmic particles. Most of the people on Earth live down in this region of the Earth, between middle of Canada and the top 3/4 of South America and all the way around the Earth. That's where most of the people of Earth live. Like 99% of the Earth's population lives there. And as particles come in towards this region, they get turned. They get bent by the magnetic field of the Earth, and they follow the field lines to the North and South Pole. North and South Pole are bombarded constantly with these cosmic rays. And if you've ever seen people that are working on the North and South Pole, they're covered with many layers of protection, not just because it's cold, but also because of cosmic particles. They don't go outside much. They often wear foil suits that look like space suits. But one of the reasons for this is to protect them from these high energy cosmic particles that can cause damage to the human body. And those things, if those things were bombarding the Earth constantly, it would be destroying our atmosphere, destroying life on Earth. I mean, Earth wouldn't exist as a life-bearing planet without its magnetic field. Magnetic field redirects most of those particles. Most of the particles never even hit the Earth, but the ones that do hit at the poles, and most of them just kind of bend around the Earth's magnetic field and go off into space somewhere else. They go off and hit Mars, which doesn't have a very strong magnetic field. Or they go off and hit some other thing that doesn't have a very strong magnetic field.
Can the magnetic field of Earth switch?
Yeah, it has switched many times in history. Yeah. But as long as it's there, we're fine. Here's the Fermilab accelerator. This is actually down inside the particle accelerator, which is down underground, several stories. and it's I think they've got 2 miles of accelerator underground. What's that?
In Illinois.
Yeah, it's right outside Chicago. The bigger one, which is the Large Hadron Collider it's on the border between Switzerland and France. It's something like 12 miles or 14 miles of underground accelerator. It's much, much bigger. But they use magnetic fields to steer these particles and to accelerate these particles around and around and around these accelerators, and then they run them into each other and see what comes out. But the whole purpose of this is to break down particles smaller and smaller and smaller, see what the smallest thing is out there, and see what we don't know about the microscopic microverse or whatever. And if you do have a chance to tour Fermilabs, I highly recommend it. It is a phenomenal research facility, and they have all kinds of cool, interesting things to see. It's great for families and kids, lots of activities for them to see there as well. If you're ever in Switzerland and you have a chance to see the one there, highly recommend that. Here's an interesting device called a tokamak, and these are becoming more and more common in the world as people are trying to study fusion energy. What a tokamak does is it uses a toroidal electromagnet. So a toroidal electromagnet is an electromagnet wrapped around a donut shape all the way. So this wire would be wrapped all the way around, and sometimes in many different directions, and sometimes magnets in other directions on the outside and everything else. But the purpose of this magnet is to contain a high energy plasma, essentially to contain a really powerful fire inside. And what they're trying to do is they're trying to recreate the processes on the sun inside of this container. But the problem with doing that is you have to contain it. As you create this plasma, it wants to escape and destroy things. So you have to contain it using magnetic fields. And they use these toroids to do that. And if we can successfully and efficiently and effectively contain these things, then we can create energy like the sun does and not have to worry about burning coal or using nuclear fuel or anything else. It would be a phenomenal thing if we could get it done. We just haven't been able to do it in such a way that it's inexpensive yet.
Doesn't sound cold.
What's that?
It doesn't sound cold.
Doesn't sound cold? Well, you're talking because they call it cold fusion. This is called cold fusion because it's much colder than the sun. So they're trying to recreate the things going on in the sun without getting as hot as the sun does. So the way to do that is to contain it and create a high pressure environment instead of a high temperature environment. Yeah, so it's definitely not cold, but it's much colder than the sun, which is why they call it cold fusion. So right here is an equation you should remember, because this is going to tell you the radius that a charge of mass m at velocity v with charge q is going to be moving in a magnetic field B, and this is definitely a question you will be asked in your homework.
So the mass and the velocity of the particle over
The charge, they're all to do with the particle, and then B is the magnetic field that you put that particle in. So they're going to ask you things like, this electron enters a magnetic field of 3 Teslas, and it's going at a velocity of 500,000 meters per second. What is the radius of its orbit? That kind of thing, right? You know the charge of the electron, you know the mass of the electron, you know the magnetic field it's in, you know the velocity, plug them in, we're good to go. Or they might say a particle is injected into a magnetic field and it has a radius of its orbit that is this. What is the charge to mass ratio? They might ask you that. So they can ask different things using that equation, and all very practical, useful things. Okay, 22.6, the Hall effect. What time is it? 10:34. I think we have time to do this. So the Hall effect is something that happens when you put a conductor inside of a magnetic field. And it shouldn't be surprising that this happens, because we already know that charges, when they're moving in an electric field, are affected, they feel a force. So what if we put a conductor that has a current going through it in a magnetic field? Will it feel a force on it? It will. And so here's a conductor, and if you have a current going to the right, that means that effectively positive charges are moving to the right. Really what's happening is negative charges are moving to the left, but neither here nor there. And if the magnetic field is coming out of the page, represented by these dots, what is the force that this wire is going to feel on it? Well, we put our thumb in the direction of the electrons moving to the left, and we put our hand in the direction of the magnetic field coming out of the page, and that means that the electrons are going to feel a force into the page. Wait, does that? No, that's not right. It's this way. Oh, fingers in the direction of the field coming out, right? Okay. So we put this right-hand rule always messes me up. And it will you'll always find a right-hand rule that confuses you because there's too many of them. But the thumb in the direction of the velocities, which is to the left, then our fingers point out of the page, coming out of the screen, and that means the palm of our hand is pointing up, which is the direction a positive charge would feel force. That means that the electrons are going to feel a force going down, right? However, if we let's see.
You got me confused now. Start over on the hand thing.
Dad,
What?
I'm gonna tattoo my thumb with current. My finger with.
You can get some tattoos. Just get make some little Sharpie tattoos on your hands. I've actually known students that have marked their hands up for the right hand rule. So
I just think it'd be like the nerdiest set of tattoos.
I'm sure. So let's see if somebody's done it.
Are you 18? Yes. I got money.
Right hand rule
Oh, really?
tattoo. See? Got right hand rules. Someone's going on his foot. But this is a right hand rule for spin. Right hand rule tattoo. Let's see who's got another one that's physics based. Start looking at tattoos. You might encounter some weird things online. But definitely there's a right hand rule, because there's a right hand rule for spin, so he's got the right hand rule for spin on his wrist. But I think you're right. Putting it on your hand would make no sense.
I'm going to do it specifically with areas, so I know which way to point everything. Oh, it's going to be so much easier. Like, oh,
How do you spell tattoo? That's not how you spell
You
tattoo.
put two T's on the center.
Oh.
I got time.
I'm only seeing the one right hand rule tattoo, unfortunately. Somebody's got a molecule on their hand. Some strange tattoos out there.
So what we're learning is that some people are nerdy, but just not this nerdy.
Yeah.
What does that star tattoo mean? I've never figured that out. I've seen multiple people have it.
I don't know. I'm not a tattoo person. I could care less about tattoos. I think people who have tattoos just have too much money and not enough sense. Tattoos are expensive. Holy crap. You ever seen people? I have a friend who works here at the college. He's got thousands of dollars worth of tattoos on his body. I'm like, what? Is it really worth it? Thousands of dollars? Are you kidding me? I mean, I've got scars that cost me hundreds of dollars medically, but I couldn't avoid those.
I got a few of them too.
Yeah, you've probably got more than the average person. But anyway, in the end, we don't use the direction of the electrons because we don't. When we're talking about flowing charge, we don't talk about electrons. We talk about current. So in the end, we're going to use we're going to put our thumb in the direction of the current. We're going to talk about the flow of positive charge because it has the same effect. So we're going to talk about the flow of positive charge. We're going to put our thumb in the direction of the current, our hand in the direction of the magnetic field, and our palm will point in the direction of the force on the positive charges. But what the Hall effect does is it actually forces the positive charges to one side of the wire and the negative charges to the other side of the wire. Okay? That's what it does. It's plain and simple. So, effectively what it does is the electrons end up on one side of the wire and bare, ions end up on the other side. But the Hall effect is this separation of charges which creates an electric field across the conductor. That electric field can be measured so that you can use a conductor, put a conductor with a current inside of a magnetic field, and you can measure the magnetic field that way by measuring the charge separation and by measuring the electric field in between them. And so in the end, you're creating an EMF, you're creating an electric field in the conductor, or a voltage across the conductor, which can be calculated by the magnetic field strength times the length of the conductor that is in the magnetic field that is perpendicular to the magnetic field, times the velocity of the conductor through the magnetic field, or the velocity of the charges through the magnetic field. And this is used all the time to calculate magnetic fields. We have things called Hall probes, which we move through a magnetic field, and as it moves through the magnetic field, it creates this EMF across the conductor.
But they all have to be perpendicular.
Yeah, you just move it through perpendicularly, and it can measure the magnetic field by calculating the EMF. So it's called a Hall probe. Well, we're done. We're done with the first 6 sections. Tomorrow in our lab, we're going to put a lot of this stuff into practice. We're going to create magnetic fields. We're going to measure magnetic fields. We're going to detect magnetic fields. We're going to do all kinds of magnetic field stuff tomorrow. So we will see you tomorrow. Have a good day. Do I have a homework assignment for this one yet? I don't know either. So chapter 20, what is this? 3? 22. I do have a homework assignment. It only has 27 problems, man. Sweet.
Come on, man.
Well, most of what we've covered so far was concept or
Yeah.
step equations.
I'll tell you what, I'll look at it and I'll make sure that I want to keep all those questions. I'll erase ones that I want to keep right now so that we're not trying to fix it during the assignment, since nobody started the assignment yet.
Can you promise us that you'll erase one question?
No.
Sorry, I tried.
Yeah. I know you were going to say that.
I did too. But no, I can also say that I tried, so you can't.
What the heck?
I know.
This has nothing to do with what we're doing.
Nothing at all.
I'm going to erase that one.
Nice.
Okay, so.
Ha! Like the first 7.
Oh, none of these are all friction questions from last semester. So I haven't put any questions in this assignment yet.
Oh, so we messed on.
Let me go erase all those questions. 22 questions. We will remove all of them.
I'm gonna go hole punch my textbook.
I'm going to go schedule my exam for tomorrow.
Oh yeah, I didn't do that too.
Yep. Go visit your mom.
Well, that's where I was gonna hold
Uh-huh.
She's my right home.
You need to go visit her today.
Yeah. But not for a while. She's still for a while.
Because I was looking at it and I was like, wait a second.
I figure.
Okay, so I will create a new assignment for you guys that will be ready.
Say that again?
I will create a new assignment for you that will be ready by the end of today so you can get started.
I'm so happy I start my second shift job Friday.
Nice.
Thursday I'll still be tired, but after that, be back to normalcy.
Okay.
See you later.
See you.